Yo, yo, I think bro is streaming. Yo, 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 yo. Okay, for now though, play peak. What? What I play, man? What I play, bro? What? What? Oh nah, bro. What? Okay. Dang. Wait, I'm gonna look at my settings for because what the fuck? Stream settings. Hell nah. What the hell? Wait. What the fuck? Hmm. Well, I'm gonna look up something. Oh, okay. Play Roblox, bro. This is so cringe. Okay. We roll. First up. Butcher. I'll play Butcher. Okay. Thunderstruck. Oh nah. ACDC. Oh nah. Bro, I'm so shit at guitar, man. Fuck. Seven. Oh, fuck my ears. I don't know how to play ACDC, bro. Like, I don't know how to play AMAC. No. Oh my shit. No, it's racist. I don't know how to play, bro. I don't know how to play that, bro. I only know how to play. No. I think that's the wrong one. What? Okay. No. 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 Oh no, man. I'm just gonna do this. I don't know what the fuck I'm doing. Okay. Bro. Butcher. What is? What is this capturing? We'd have to create a new one only. Window capture. Yes. Yes. Okay. Oh nah. You keep hearing. Yes. On my ears. Okay. Study BE. Oh hell no. Hell nah. I mean, you have DE, but it's not really that hard, man. And you study a bit. You don't. No, hell nah. Oh, it's so cringy, bro. Oh, it's for. The hell is this? This? Okay. 2 likes. Oh, hell nah. Bro is big. Bro, this is okay. Fuck. Oh nah, I swore, bro. I have no monetization now, bro. Fudge. Huh? It's too loud. Imagine you get an ad. Bro, I have YouTube Premium, man. is the delay? One hundred. Oh nah. Huh? 110? Oh nah. And you're my number one fan, bro. Holy shit. 50 XP. I'm gonna use it on my amp instead with my ears. It's too loud. A grinder. Oh nah. I think bro's gay. Oh nah. Okay. Oh shit, my ears. Why is this so clean? It's too clean. My tone is too clean. My tone is too clean. My tone is too clean. Huh? There. Okay, there.
what's up, you guys? Nut. These things here are called the pickups. They pick up the sound. And so this fun little switch right here controls the pickups. Now, the pickups in different parts of the guitar have different sound qualities. So when you have a selector with this style of guitar, each switch here is a different configuration of the pickups. For instance, if I'm flipped up all the way here, it's only picking up sound from this pickup. If I do it in the middle, it's from both. And when I go to the back, I'm going to start with a light or a medium pick. It's more forgiving and it's great for a beginner. So that's what I would recommend. Also, we've got the strings here. We've got these things called power chords, which sound like this. So the first thing I would try and do is have you just see if you can just pick down the tip of the pick. Think of it as you've got your thumb, and you can just put it as an extension of your, underneath your thumbprint, like it's extending out like your thumbnail. And then with your index finger, you just pinch it together. And then I tend to tilt it to my left a little bit. But really, you got the thumb, and then it just tilts to the side of your thumb a little bit. But it's meant to be what feels comfortable for you. Our hands are all shaped a little differently, different sizes. But I grab the pick, and I'm going to strike down and see if I can just strike that top string there, the E string, as in Eddie Ate Dynamite, Goodbye Eddie. Now you're going to be accidentally hitting the other strings when you start, but that's okay. But you want to just start seeing if you can hit the strings all alone. You can look down at the string and then see if you can do it with the next one. And then keep going and just start targeting out those strings. I know it's not very exciting, but that's a starting point. And you're going to need to be able to do that to tune your guitar at the very beginning anyway. So now I recommend a couple little classic little one string kind of riffs. Now the first one I ever learned sounded like this. So what I'm going to do is I'm going to show you a little bit different one. We're going to go like this, and I'm going to say the fret names. Now the spaces in between here are called frets. So if I said first fret, you're going to take your finger, and we're just going to talk about this Eddie Ate Dynamite, Goodbye Eddie. We're going to just talk about this top E string here. So if I said play the first fret on the E string, you'd count up to that first section and use the very tip of your finger and press down on the string and see if you can get it to ring out. Should sound like this. Now if you're scooted back on the fret. All right, this is a cheater, super beginner, easy for beginners way. Did I mention beginner? Cashmere for Led Zeppelin. This will just help your technique, and it's very recognizable. You're gonna aim for this D string, 1, 2, 3 down, and then put your index finger on the second fret G string.
Kutupag. Agne. But now let's take a break from this. A bit hard, yes.
Hey, how you doing? Justin Sandico here, and welcome to the best beginner guitar course ever. I've spent over a year creating this course, and I'm confident it's... Hey, how you doing? Justin back with you today to talk about your practice schedule for lesson 4. So, we're starting off with 2 minutes on your finger stretch exercise. Remembering to just keep it real slow. Just 2 minutes right at the beginning. Get your hand warmed up. Don't press too hard and wear your hand out. It'll make the rest of your practice session a little bit painful, okay? So 10 minutes working on that exercise. Then we're going to have 1 minute on your D minor chord perfect. So just playing the chord over and over. Put the fingers down, strum it, lift it off, put it down, strum it, over and over again. Just for 1 minute. Then for 1 minute, you've got chord perfect on whatever chord you're finding most difficult. Now, for me, it was mostly D minor again. So
Tonic, fifth, tonic, fifth, octave, major third, A to E, a fifth, a fifth, A minor, B major is the same, thinking, say just C, tonic, tonic, third, major third, major third, fifth, 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 octave, major third, C minor, is B major, C minor, C major, C minor, D, D, of course, fifth, tonic, fifth, tonic, fifth, octave, 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 and third, D minor is this. Same thinking. E major, tonic, tonic, fifth, octave, tonic, fifth, octave, third, just octave, octave, third, fifth, yeah, octave, fifth, fifth, minor, F, tonic, it's just the E, G, tonic, third, tonic, tonic, third, tonic, tonic, third, fifth, fifth, octave, fifth, octave, Next is what? 39 minutes. Okay.
Times x minus 6 to the 1 power. Now, the reason why I wanted to write it that way is so that it matches with what we see there. Now, I also have 4 to the n on the numerator of the second fraction. On the bottom, I have 4 to the n plus 1, which I'm going to write that as 4 to the n times 4 to the first power. And then I also have this expression, x minus 6 raised to the n minus 1. So I can cancel x minus 6 raised to the n minus 1, and also 4 raised to the n. At this point, I'm going to separate it into two separate absolute value expressions. So this is going to be one of them. So we have the absolute value of n plus 1 over n, and then for the other expression, x minus 6 over 4. Now, as n goes to infinity, what happens to n plus 1 divided by n? That goes to 1. This one is insignificant when n becomes very large. And so you're going to get n over n, which is 1. So what we now have is 1 times the absolute value of x minus 6 over 4, which we can write that as 1/4 absolute value x minus 6. And because we're dealing with the ratio test, and we want to find the x values where this series will converge, we need to set it less than 1. So if we multiply both sides, if the x values, because we're dealing with the ratio test, and we want to find the x values where this series will converge, we need to set it less than 1. So if we multiply both sides by 4, we're going to get the same result. So 4 times 1/4, that's 1. And so we have the absolute value of x minus 6 is less than 4, which means x minus 6 is between 4 and negative 4. Adding 6 to all three sides, 4 plus 6 is 10, negative 4 plus 6 is 2. And so as you can see, the interval of convergence is the same for f of x and f prime of x. The only thing that may be different are the endpoints. So let's write the original series for the first derivative, which we found it to be this. So here's the question for you. When x is 2, will the series converge or will it diverge? So this is going to be n. 2 minus 6 is negative 4 to the n minus 1 over 4 to the n. So we have negative 4 to the n minus 1. We can write that as negative 4 to the n times negative 4 to the negative 1 power over 4 to the n. So we can write negative 4 to the n over 4 to the n as negative 4 over 4 raised to the n. And negative 4 to the negative 1 power, that's basically 1 over negative 4 to the first power. So by moving negative 4 to the bottom, the negative exponent becomes positive. Negative 4 divided by 4, that's negative 1. So we have negative 1 to the n, and then times, or just divided by negative 4. Now, I'm going to rewrite it like this. Negative 4 is basically 4 times negative 1. So now we have n times negative 1 to the n times negative 1, which is negative 1 to the first power, over 4. So this is negative 1 to the n plus 1 times n divided by 4. So notice the negative 1 to the n plus 1. That tells us that we're going to have alternating signs in the series. So we have an alternating series, which means we need to use the alternating series test to see if it's going to converge or diverge. Now, for the alternating series, our a sub n is everything except this portion, which alternates the sign. So our a sub n is n over 4. The first thing we need to do is make sure that it passes the divergence test. So the limit as n approaches infinity for a sub n, it has to equal 0. So let's see if it does. As n goes to infinity, what happens to n divided by 4? Infinity divided by 4 is still infinity. So therefore, it does not pass the divergence test, and as a result, it will not pass the alternating series test. So this series diverges when x is equal to 2. So 2 is not included in the interval of convergence. So we're going to use a 2 in parentheses as opposed to a bracket. So now what about when x is equal to 10? The divergence test. So the limit as n approaches infinity for a sub n, it has to equal 0. So let's see if it does. As n goes to infinity, what happens to n divided by 4? Infinity divided by 4 is still infinity. So therefore, it does not pass the divergence test, and as a result, it will not pass the alternating series test. So this series diverges when x is equal to 2. So 2 is not included in the interval of convergence. So we're going to use a 2 in parentheses as opposed to a bracket. So now what about when x is equal to 10? Let's see what's going to happen. So we're going to have n, and then 10 minus 6 is positive 4. So positive 4 to the n minus 1 over 4 to the n. So 4 to the n minus 1 over 4 to the n, we need to subtract the two exponents. N minus 1 minus n is just going to be minus 1. The 4 to the n's will cancel. And so we're going to get n times 4 to the negative 1 power, or simply n over 4. So what test should we use to see if the series will converge or diverge? The most easiest one to use is the divergence test. If we take the limit as n goes to infinity for n over 4, we know it's going to be infinity. And so the series diverges. So it diverges at 2 and 10, but it converges between 2 and 10. So f prime of x and f of x for this particular example have the same interval of convergence. Keep in mind though, the endpoints may vary. Sometimes they're the same, sometimes they're different. So now let's move on to the integral of f of x. So let's start with the original power series. And then let's find the integral of f of x dx. So we need to use the power rule. So we're going to add 1 to n. So this is going to be n plus 1. And then we're going to divide by n plus 1. Now 4 to the n is a constant, so we're just going to rewrite it exactly where it was. So this is our new series. Now, if you perform the ratio tests on this series, following the same steps that we employed for f of x and f prime of x, you're going to get the same inequality from 2 to 10. The only thing we need to do now is we need to check the endpoints, 2 and 10. So let's go ahead and plug in 2 into the power series. So this is going to be 2 minus 6, which is negative 4, to the n plus 1 over n plus 1 times 4 to the n. So what does that simplify to? So this is going to be negative 4 to the n times negative 4 to the first power over n plus 1 times 4 to the n. So if we divide these two, negative 4 divided by 4 is negative 1. And so that's going to be negative 1 to the n power. And then we have negative 4 over n plus 1. Negative 4, I'm going to write that as 4 times negative 1 to the first power. So we can write the series like this. It's going to be negative 1 to the n plus 1 times 4 over n plus 1. So will the series converge or will it diverge? What would you say? Negative 1 to the n plus 1, that tells us that we have an alternating series. So will it converge or will it diverge? So let's perform the divergence test. So if we take the limit as n goes to infinity for a sub n, which is everything except this part, so that's 4 over n plus 1, what's going to happen? When n becomes very large, 4 over n plus 1, that's going to go to 0. So it passes the first part of the alternating series test. Now for the second part, we need to show that a sub n is a decrease in sequence. So a sub n is 4 over n plus 1. And the next term, a sub n plus 1, that's going to be 4 over n plus 2. 4 over n plus 2 is always less than 4 over n plus 1. So by the alternating series test, this series converges. Is everything except this part. So that's 4 over n plus 1. What's going to happen? When n becomes very large, 4 over n plus 1, that's going to go to 0. So it passes the first part of the alternating series test. Now for the second part, we need to show that a sub n is a decrease in sequence. So a sub n is 4 over n plus 1. And the next term, a sub n plus 1, that's going to be 4 over n plus 2. 4 over n plus 2 is always less than 4 over n plus 1. So by the alternating series test, this series converges. So therefore, 2 is included in the interval of convergence for the integral of f of x dx. So it's a little different than the last two. Now let's rewrite our power series. So what about if x is 10? Will the power series converge or will it diverge? So let's plug in 10. 10 minus 6 is 4. So we're going to have 4 to the n plus 1, which I'm going to write that as 4 to the n times 4 to the first power over n plus 1 times 4 to the n. So we can cancel 4 to the n. And so we're left over with this particular series. So will the series converge or will it diverge? What would you say? For this example, I'm going to use the integral test. So let's integrate the corresponding function from 1 to infinity of 4 over x plus 1. So this is an improper integral, so we need to write the limit as some constant, which we'll use b, goes to infinity, and the antiderivative of 4 over x plus 1, that's 4 times the natural log of x plus 1 from 1 to b. So that's going to be the limit as b goes to infinity, and then we're going to have 4 ln b plus 1 minus 4 ln 1 plus 1, which is 2. So as b goes to infinity, what happens to the natural log of b plus 1? The natural log of infinity is still infinity. So this is going to be 4 times infinity, which is still infinity, minus some constant, which is going to be infinity. So because the integral test gave us infinity, then the series diverges when x is 10. So 10 is not included. So therefore, this is the interval of convergence for the integral of f of x dx.
So we're told here that f of x is equal to this infinite series, and we need to figure out what is the third derivative of f evaluated at x equals 0. And like always, pause this video and see if you can work it out on your own before we do it together. All right, so there's two ways to approach this. One is we could just take the derivative of this expression while it's in sigma notation. The other way we do it is we could just expand out f of x and take the derivative 3 times and see if we get an answer that, I guess, makes sense. So let me do it the second way first. So let me just expand it out. F of x is equal to, let's see, when n is equal to 0, this is negative 1 to the 0, which is just 1, times x to the 0 plus 3. So it's going to be x to the third over 2 times 0, so that's 0 plus 1 factorial. So that's just going to be over 1. Then the next term, when n is equal to 1, well, now it's going to be negative 1 to the 1, so now it's going to have a negative out front. Negative, and there's going to be 2 times 1 plus 3. So that's going to be x to the 5th power over 2 times 1 plus 1. So it's going to be 2 plus 1 is 3 factorial. So it's going to be x to the 5th over 6. And then when x is equal to 2, this is going to be positive again. It's going to be x to the 7th power, over 5 factorial. Is that right? Yeah, 5 factorial. And 5 factorial, actually, let me just write that out as 5 factorial. 5 factorial would be, what? It would be 120. It would be 5 times 4 times 6. So it would be 120. But we could just keep going, minus, plus, and it goes on and on and on forever. Well, now let's just take the derivatives. So f prime of x is going to be equal to, we're just applying the power rule here, it's going to be 3x squared minus 5/6 to the 4th plus 7 over 5 factorial x to the 6th. I'm just applying the power rule. Minus, plus, we just keep going on and on and on forever. The second derivative, f prime prime of x, is going to be equal to, apply the power rule again. It's going to be 6x to the 1st minus 4 times 5 over 6. I'll just write that as 20 over 6, x to the 3rd, plus 6 times 7, so it's 42 over 5 factorial x to the 5th, and we're just going to keep on going, minus, plus, keep going, or alternate between minus something, then plus something, on and on and on forever. And then we get to the third derivative. The third derivative is equal to, let's see, the derivative of 6x is 6, and then we have minus 20 times 3 is 60 over 6, which of course is 10, x squared, plus 5 times 42 is what, 210 over 5 factorial times x to the 4th power minus plus over and over and over again. And then we just evaluate this at 0. F prime 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 at 0. Well, when x is equal to 0, all of these terms with x's are going to go to 0, and you're just going to be left with this. Man it out, but we could have said f prime of x is equal to the sum from n equals 0 to infinity. And you take the derivative here, you're going to get, and you're taking the derivative with respect to x. So for that purpose, you assume everything else is, well, the n is just going to tell us which term is going to tell us how we change from term to term. So if we take the derivative with respect to x here, use the power rule, bring the 2n plus 3 out front. So it's going to be negative 1 to the n times 2n plus 3 times x to the, decrement the exponent, 2n plus 2 over 2n plus 1 factorial. And then if you wanted to take the second derivative, and this is the same thing as this. If you take the second derivative, f prime prime of x, well, now we're taking the sum from 0 to infinity of negative 1 to the n. Let me move over to the right a little bit so we have some space. And now we take this exponent out front. So you're going to have 2n plus 3 times 2n plus 2. All of that's going to be over 2n plus 1 factorial. And this is going to be times x to the 2n plus 1. All I'm doing every time, it seems really complicated, I'm just taking the exponent out front, multiplying it out front, and then decrementing it. So 2n plus 2 minus 1 is 2n plus 1. And then if I want to take the third derivative is the sum, n equals 0 to infinity, negative 1 to the n. We take this, bring it, multiply it. So we're going to have 2n plus 3 times 2n plus 2 times 2n plus 1. All of that over 2n plus 1 factorial. And then that is going to be times x to the 2n power. Now let's now evaluate this thing when x is equal to 0. So f prime 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 of 0 is going to be the sum from n equals 0 to infinity of negative 1 to the nth power. Now this is going to be interesting. We're going to have all this business, 2n plus 3 times 2n plus 2 times 2n plus 1, all of that over 2n plus 1 factorial times 0 to the 2n power. Now you might be tempted to say, well, hey, if 0 to these different powers, maybe everything's going to be 0.
No.
But remember, we're starting at n equals 0. So for
0.
any n that's not equal to 0, this 0 to that power is just going to be 0, and that term's going to disappear, kind of like what we saw when we expanded it out. And so the only term that matters here is when n is equal to 0. And so this is just going to be equal to, because for n equals 1, 2, 3, 4, 5, all the way to infinity, this thing is going to dominate. It's just going to multiply. It's going to be 0, and you're just going to zero everything out. And so this is just going to reduce to the first term when n equals 0. And when n equals 0, it's going to be negative 1 to the 0. This is going to be, which is just 1. So let me just write that as 1 times, this is 3 times 2 times 1 over 1 factorial. And then times 0 to the 0, which is equal to 1. So this is equal to 1, and so this is equal to 6. So either way, I think the first way we did it was a little bit more straightforward, a little bit more intuitive, closer to what you might have seen before. But it's important to realize that we did the same thing both times. We just kept it in the sigma notation on this time to the right. And this technique is useful because You'll see it a lot in math, where you might want to do things in a little bit more of a general way. And so it might be helpful to take the derivatives while you stay in that sigma notation. Nth derivative of g at x equals 0 is given by, so the nth derivative of g, evaluated at x equals 0, is equal to the square root of n plus 7 over n to the third for n is greater than or equal to 1. What is the coefficient for the term containing x squared in the Maclaurin series of g? So let's just think about the Maclaurin series for g. So if I were to have my function g of x, the Maclaurin series, I could say approximately equal to, especially if I'm not going to list out all of the terms, is going to be equal to, well, it's going to be equal to g of 0 plus g prime of 0 times x plus g prime prime of 0 divided by, I could say 2 factorial, but that's just 2, times x squared. And that's about as far as we go, because we just have to think about what is the coefficient for the term containing x squared. I could, if they said what's the coefficient for the term containing x to the third, I would keep going. I'd go g prime, I would take the third derivative evaluated at 0 over 3 factorial. I could view this as a factorial too, but that just evaluates to 2. I could view this as 1 factorial. I could view this as 0 factorial, just so you see it's a consistent idea here. And I could, of course, keep on going. But we just care about, they're just asking us, what is the coefficient for the term containing x squared? So they just want us to figure out this. What is this thing right over here? So to know that, we need to figure out what is the second derivative of g evaluated at x equals 0. Well, they tell us that over here. It's a little bit unconventional, where they give us a formula, a general formula for any derivative evaluated at x equals 0. But that's what they're telling us here. So in this case, the n isn't 0. The n is the derivative we're taking, and that's going to be our second derivative. So this is, so if I wanted to figure out g, if I am figuring out the second derivative, and I could write it like that, evaluated at 0, or I could write it like this, just so the notation is consistent. I could write it like that. The second derivative evaluated at x equals 0 is going to be equal to, well, our n is 2. So this is going to be the square root of 2 plus 7 over 2 to the third power. So 2 plus 7 is 9. Take the principal root of that. It's going to give us positive 3 over 2 to the third, which is 8. So this part right over here is 3/8. So the whole coefficient is going to be 3/8. That's this numerator, divided by 2, which of course is equal to 3 over 16. And we're done. They didn't want us to figure out a couple of terms of this, which we could call the Maclaurin polynomial, an nth degree Maclaurin polynomial. They didn't want us to find the entire, keep going with this series. They just wanted to find one coefficient right here, the coefficient on the second degree.
In this video, we're going to talk about how to find the Taylor series and the Maclaurin series for different functions. So let's start with this example. Let's find the Taylor series given the function f of x is equal to ln x centered at c equal 1. So what we need to do is basically write out the first 4 derivatives. So f prime of x, the derivative of ln x, that's 1 over x. Now to find the second derivative, we need to rewrite it and then
Salve, sono di Londra, Roma.
Lauro.
Scusa, tu sei di Londra, vero?
Ciao, tu sei di Roma, vero? Tu sei di Roma, vero?
Scusa, tu sei Anna, vero? Scusa, tu sei di Roma, vero?
Scusa, tu sei di Filadelfia, vero?
Io sono di Roma. Piacere. Io sono Roma. Di Roma. Piacere.
Nice to meet you. Piacere, piacere, nice to meet you.
Scusa, tu sei di Milano, vero?
Io sono di Milano, piacere. Io sono di Milano, piacere.
Piacere.
Piacere. Piacere.
Arrivederci.
Arrivederci, Matteo.
De nada, Luis.
Hablo.
Gracias. Buenas noches.
Sí, yo hablo
Hablo.
español.
Lo siento.
Ah, sorry. Yo hablo inglés.
Inglés.
De nada, Juan.
Lo siento, perdón.
Perdón. Por favor, no. Por favor, no.
Please, no.
Gracias. Adiós.
De nada es.
Sí, yo soy Juan. Sí, yo soy Juan.
Sí, gracias.
No. No. It's a rainy brew. It's a rainy brew. Kokoro nagasu namida. Dum 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 dum.
Ich bin groß.
Ich bin sehr nett.
Es. Lag.
Mein Mann ist klug. Meine Frau.
Meine Frau ist klug. Meine Frau ist klug. Mein Bruder ist nett.
Bruder.
Meine Tochter.
Meine Tochter ist sehr klug. Meine Tochter ist sehr
Tochter.
groß.
Klug.
Meine Schwester ist nett. Schwester ist nett.
Meine Mutter ist groß.
Mein Bruder ist sehr groß.
Meine Mutter ist nett und groß.
Get more with Super Duolingo. Go ad-free and
Du.
Du bist nett.
Bruder.
Mein Bruder ist sehr nett.
Meine Mutter ist nett und groß. Mutter ist nett und groß.
Mein Bruder und mein Mann.
Mein Mann und meine Mutter. Mutter und meine. Mann und meine Mutter. Mein Mann und meine Mutter.
Meine Schwester und mein Mann.
Ein Vater und eine Mutter. Vater und eine Mutter.
Du bist mein
Vater.
Eine Mutter und ein Vater. Mutter und ein Vater.
Eine Mutter.
Eine Mutter, ein Vater. It's a rainy blue, it's a rainy blue. You let it go, nagasu namida. Rainy blue, loneliness. It's a rainy blue. Bach.
R.
R.
R. V.
V.
V. R. V. V. R. R. V. V. Yo.
Yo. Yo.
Yo.
The hell?
Yo.
Hall.
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 Hall. Hall. Yo. Leo. 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 Luit.
Лед.
Люд.
Lut. Рьот.
Рьет.
Ла.
Лад.
Лед.
Век.
В. К.
Рак. Рак.
Р. Йо. Х. В. Р.
Рот.
Pot. Ja, pot.
Док.
Да. Да.
Так. Кот. Кот. Тога.
Кода.
Кода. Тоже.
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 Иди.
Иди.
Идоль.
Идол.
Ода.
Ода.
Дата.
Дата. Дата.
Д. От. А.
Идиотка.
Идиотка. Кидает. Кидает.
Кидает.
Кидает.
Диктат. Диктат. Тик.
Див.
Идти. Идти. Idź.
Idź. Idź. Idiotka. Idiotka. Idiotka.
Coda.
Tože. Dek. Tata. Idiot.
Тоже.
Kidok.
Idyllik.
Idyllik. Idyllik. Diktat. Ideal. Jedok. Itti.
Colli.
And use the power rule. So the second derivative is -1 divided by x squared. And then to find the third derivative, let's use the power rule again. So for the third derivative, it's going to be 2 divided by x cubed. And then to find the fourth derivative, it's going to be -1 times -2, that's +2. And then we need to take the derivative of x to the -3rd power. So that's -3x to the -4. So the fourth derivative is -6 divided by x to the 4th power. Now the next thing that we need to do is evaluate the function and the derivatives at c. So f of 1, c is 1, that's going to be ln1. The natural log of 1 is 0. And then f prime of 1 is going to be 1 over 1, which is 1. And then the second derivative, evaluated at 1, that's -1 divided by 1 squared, which is just -1. And for the third derivative, it's going to be +2. And the value for the fourth derivative, when x is 1, is -6 divided by 1 to the 4th, or simply -6. So now we can get rid of this stuff. Now this is the formula that you want to use to write the expanded form of the Taylor series. So it's f of c plus f prime of c times x minus c to the 1st power plus f double prime of c times x minus c to the 2nd power divided by 2 factorial plus the third derivative evaluated at c times x minus c to the 3rd power divided by 3 factorial, and then it just continues. So f of x, which is ln x, we could say that it's equal to f of c, which is f of 1, and we know that f of 1 is 0, and then plus f prime of c, which is 1, times x minus c, c is 1, and then the second derivative, that's going to be -1, so that's f double prime of c times x minus c to the 2nd power divided by 2 factorial, and then for the third derivative, that's going to equal 2, so that's going to be plus 2 times x minus c to the 3rd power divided by 3 factorial, and then we have -6 x minus c to the 4th power divided by 4 factorial, and then that's going to continue. Now let's simplify what we have. So we don't need to write 0. So we could say that the natural log of x is x minus c to the 1st power divided by 1 factorial, and then minus, well, I need to get rid of the c. This is supposed to be x minus 1 to the first power. And then it's going to be minus x minus 1 squared divided by 2 factorial, which is simply 2. And then plus, what is 2 divided by 3 factorial? 3 factorial is 3 times 2 times 1. And so we can cancel the 2. So therefore, this is going to be plus x minus 1 to the third power divided by 3. I'm just going to write this as 1 so you can see the pattern. And then we're going to have, this is going to be negative. Now, 6 divided by 4 factorial. Let's simplify that. 4 factorial is 4 times 3 times 2 times 1. So 6 will cancel with 3 times 2. So this is going to be x minus 1 to the 4th power divided by 4. So now we could see a pattern developing. So how can we write this series using summation notation? So let's start with n equals 0, and we're going to go to infinity. So when n is 0, we need to get 1 as an exponent. When n is 1, we need to get 2. And when n is 2, we need to get 3. So therefore, it's always 1 more than our n value. So we're going to have n plus 1. So this is going to be x minus 1 raised to the n plus 1 power. And since these numbers are the same, we need to have an n plus 1 expression on the bottom. Now the last thing we need to deal with are the alternating signs. It's going to alternate from positive to negative to positive and so forth. So we can either use negative 1 to the n or negative 1 to the n plus 1. Which one should we use?
N plus 1.
Now when n is 0 for the first term, we need to get a positive sign. Negative 1 to the 0 power is positive 1. So we need to use this one. And so I'm going to write that here, negative 1 to the n. So this is the Taylor series for the function ln x centered at c equal 1. And you can see the x minus 1 term, which tells us that it's centered at c equals 1. For the sake of practice, let's go ahead and try another example. So find a Taylor series for the function f of x equals e to the x centered at c equals 3. So go ahead, pause the video, and take a minute to try this problem. Just like before, let's make a list of the function and its derivatives. So we have the function e to the x. The first derivative is going to be e to the x, as well as the second, the third, and the fourth. So all of the derivatives will be e to the x. Now, f of c, which is basically f of 3, that's e to the 3, and that's going to be the same as f prime of 3, f double prime of 3, and all of the derivatives, they will all be equal to e to the third power. Now let's write out the function. So f of x is going to equal f of c plus f prime of c times x minus c to the first power plus the second derivative times x minus c to the second power divided by 2 factorial, and then it's going to be the third derivative times x minus c to the third power over 3 factorial, and then that's just going to continue. So our f of x is e to the x, and f of c, or f of 3, that's e to the third power. F prime of c is going to be the same thing, e to the third power, but times x minus c, where c is 3, and then f double prime of c is also going to be e to the third power, and then it's going to be times x minus 3 to the second power over 2 factorial, and then it's going to be e to the 3 x minus 3 to the third power over 3 factorial. Now we need to write a general power series that will give us what we see here. So starting from 0 going to infinity, we can see that the e to the third part, it doesn't change. So that's pretty much constant. Now the only part that changes are the exponents and the factorials. Therefore, we need to represent those numbers with something that contains the letter n. The only other part that doesn't change is x minus 3 for every term. Now when n equals 0, we have the e to the third term. When n equals 1, we're going to get this term. And then this is for when n equals 2 and when n equals 3. And so notice that the n values matches with the exponents and the factorials. So therefore we can say that this is x minus 3 to the n power divided by n factorial. And this is the Taylor series for the function e to the x centered at c equal 3. Let's move on to our next example problem. Number 3. Find the Maclaurin series for the function f of x is equal to sine x. The only difference between a Taylor series and a Maclaurin series is that c equals 0 for the Maclaurin series. So that's why there wasn't any c value given to you. Now the first derivative, which is the derivative of sine, that's going to be cosine. And then the second derivative is negative sine x. And then the derivative of negative sine, that's going to be negative cosine x. And then the fourth derivative is going to be the original sine x function. Now the fifth derivative is the same as the first, and the sixth derivative is the same as the second, and the pattern will repeat. So to evaluate f of 0, that's going to be sine 0, which is 0, and then f prime of 0, cosine 0 is 1, and then f double prime of 0, that's negative sine 0, so that's 0. And then for the third derivative, it's going to be negative cosine of 0, which is negative 1. And for the fourth derivative, sine of 0 is 0. And so this is going to be the same as the fifth derivative, and this is the sixth, the seventh, and then the eighth. Now let's write out the function that we need in order to get the Maclaurin series. So f of x is going to equal f of c, but instead of f of c, we're going to replace c with 0. So it's going to be f of 0, and then plus f prime of 0 times x minus c to the first power, so that's x minus 0 to the first power, which we can simply write x to the first power. And then it's going to be the second derivative at 0 times x squared over 2 factorial plus the third derivative at 0 times x cubed divided by 3 factorial. And then that's going to continue. So f of 0, we could see that it's equal to 0. And then f prime of 0, that's equal to 1. So we're going to have 1x, and then plus f double prime of 0, which is 0. And then the third derivative, it's equal to negative 1. So it's going to be negative x cubed over 3 factorial. And then the next term for the fourth derivative is going to be 0. And then plus the fifth derivative. So it's going to be 1 times x to the fifth over 5 factorial. And then plus 0. And then minus, for the seventh derivative, negative 1 times x to the 7 divided by 7 factorial.
Mathematics. Today we're going to begin. Welcome back to Discrete Mathematics. Today we're going to begin generating functions. Generating functions are interesting because they allow us to look at questions like this algebraically. So before, when we said x1 plus x2 plus x3 is equal to 12, where all of our x's are between 0 and 6, we'd have to use the inclusion-exclusion principle, but instead, there's an algebraic way that we can get a function. And we can take that function, extract a coefficient, and that will be our number of solutions. So, how do we look at this question? Well, what we do is we introduce this notation, and every generating function is going to be a formal power series. We'll get to that in a second. But when we take a look at x1, so let's do x1 plus x2 plus x3 is equal to 12. This means we need to choose 12 total objects. So to do that, what we're looking for is the coefficient of x to the 12. And the power is always going to be the number of ways you can choose that object. So for instance, for x1 here, we can choose it 0 times because x can be as low as 0. We can choose it 1 time, 2 times, 3 times, 4 times, 5 times, or 6 times. So this is x1 because it has to be between 0 and 6. So we're saying, okay, we're going to let the powers equal that number. And then we do it the same for the second one and the third one. So we'll just cube that because we're doing the same thing 3 times. And then we want the number of ways to get to x12. So we want the coefficient of x12. Because, say we have x3 times x4 times x5, that's the same thing as saying 3 plus 4 plus 5. And x12 is going to have all the possible combinations of getting there. So that's going to answer our question of how many ways are there to solve x1 plus x2 plus x3 is equal to 12, where all of our x's are between 0 and 6. Kind of a cool thing. In fact, here's another example. Suppose we have red, blue, and white jelly beans. How do we select 20 of them if we have to have an even amount of reds? There has to be at least 14 blue, but there's also less than 5 white. Okay, well, for our reds, they have to be even, right? So we can have 0. So I'm always going to write x to the 0 as 1. So we can pick 0. We can pick 2 of them, so we have x squared. We can pick 4 of them, so we have x to the 4. We can pick 6 of them, and we can go all the way up to pick 20 of them. We can go on for infinity if we want to, but for the sake of this example, we're only picking a total of 20, so let's not go over 20. What about at least 14 blue? Well, that means the smallest amount we can pick is 14, so x to the 14, plus x to the 15, because we can have any number after 14, so this will go all the way up to x to the 20. And we have to have less than 5 white, so that means that we can pick 0 white, or 1 white, or 2 whites, 3 whites, or 4 whites. So we can't pick 5, because it has to be less than 5. So this is the generating function for the number of ways we can select red, blue, and white jelly beans. So specifically, we're saying how many ways can we select 20 of them. So we're looking for the 20th coefficient here, the coefficient of x to the 20. But we can also take a look at any other coefficient we want. So we could see how many ways there are to pick only 17 jelly beans. If we wanted to. Of course, we don't have to, but it's available. So this is the power of generating functions. We're solving the same question for every different value of n we could ever want, all at once. So that's another good example. One more. This involves making money. So what is the generating function for ways to make n cents using pennies, nickels, and dimes? So I'm not asking for any specific amount of cents. I just want to know, okay, for any given number, how many possible ways can I make it? So, let's do pennies. We want x to the n, because that'll be n cents. So we want to deal with everything in terms of cents. So, with pennies, you can have 0 cents, or 1 cent, or 2 cents, or 3 cents, and that just goes on for infinity. With nickels, you can have 0 cents, or you can have 5 cents, or you can have 10 cents, so on and so forth. Again, we go by fives because we're dealing with cents, not with the number of nickels. We have to deal with the number of cents. And of course, for dimes, we can have 0 cents, or 10 cents, or 20 cents, so on and so forth. So if we want to say how many ways can we do 7 cents, well, we can just multiply them out and see how many ways there are to get x7. If we want to get, say, $10 million, then we can take a look at 1 billion x's, so x to the 1 billion. We can do whatever we want. So that's pretty cool. Now, what really is a generating function, though? Because we have a power series here. So a power series is basically the sum of a coefficient with the power of x. So we have a0 x to the 0 plus a1 x to the 1 plus a2 x to the 2, so on and so forth. So nicer, we can write this a0 plus a1x plus a2x squared, so on, where this a is the coefficient. So when I said, what is the coefficient of x12 of some function, then you would say, oh, that's whatever a12 is. So when we take a look at this, at these generating functions here, all of our coefficients in these generating functions are just 1. But when we multiply them out, they turn into a different number, because that's the amount of ways we can do whatever we're asked to do. So here's the thing. We have those long equations, and those aren't the nicest things to work with. So we can make them shorter. And the example I'm going to give you is 1 over 1 divided by x. And we're going to use long division to figure out what this is. Okay, so 1 minus x, we're going to divide this into 1. So if you forgot polynomial long division, hopefully this will jog your memory. But 1 minus x goes into 1 one time. So then we multiply 1 minus x by 1. We put it below, just like in long division, and then we subtract. So we get 0 plus x, because we're subtracting. Okay, so now we have x left here. So how many times does 1 minus x go into x? Well, it goes in x times. So x times 1 minus x is x minus x squared. Of course, we subtract this, and we end up with x squared. So how many times does 1 minus x go into x squared? It goes in x squared times. And you can see we can keep doing this forever. So 1 over 1 minus x is going to equal 1 plus x squared plus x cubed, so on and so forth. Okay, so this is going to generate the sequence 1, 1, 1, 1, 1, 1, so on and so forth. So every coefficient is going to be 1 in this example. So this is something that you have to know. You have to memorize this, or you have to be able to reason this out, because these are crucial. So what I'm going to show you now is not long division, but I'm going to tell you what the series looks like and what the generating or the coefficients look like. So 1 minus x to the n plus 1 over 1 minus x is the same thing as before, but it's going to stop when it gets to x to the n. So what this will look like is it'll look like a bunch of 1s until it gets to the nth term. So this is the nth term, and then it's going to be a bunch of 0s afterwards. So that's what that series is going to look like. When we have 1 divided by 1 plus x, what we end up is with the alternating series. So 1 minus x plus x squared minus x cubed plus x to the 4th, so on and so forth. So that's going to take a look like 1, negative 1, 1, negative 1, so on and so forth. When we have 1 over 1 minus a to the x, that's going to be a to the 0 plus a to the 1x plus a squared x squared plus a cubed x cubed dot dot dot. So this sequence is going to look like 1a squared, a cubed, so on and so forth. So these are very crucial ones that you need to know. Of course, you can do polynomial long division to prove this to yourself, but you don't really need to. Just take it for granted. These are right, for sure. Of course, when you have generating functions, you can also take their derivatives, because it's a polynomial, so we can use calculus. So if we take 1 over 1 minus x all squared, it's just the derivative of 1 over 1 minus x. So let's take the derivative of the power series. When we take the derivative of the power series, if you don't know calculus, don't worry about the details, just memorize the solution. Or, you can learn basic calculus too. This is going to be 0. So let's make sure I'm on the right tool here. This will be 0 because the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. So you get this nice sequence now. So this is going to be 1, 2, 3, 4, 5. So this is going to be the increasing sequence where every number is just 1 ahead of the last one. So you can use derivatives and you can get new sequences. So again, this is also another important one that you should probably know. Alright, so what if I say, okay, find the coefficient of x to the 6th in this sequence? Well, it's going to be 1, 2, 3, 4, 5, 6. It's going to equal 7. It's going to be 7x to the 6th, because it used to be just x to the 7, but then we took its derivative, so now it's 7x to the 6th. So if we want the coefficient of x to the n, it's just going to be n plus 1 in this sequence. So that's another way of looking at it. Alright. What happens when we take a generating function and then we multiply it by something? So here we have x cubed over 1 minus x. Now this can be written as x cubed times 1 over x. So, 1 over 1 minus x. So if we write out the power series, it just kind of looks like this. It's x cubed times 1 plus x squared plus x cubed, goes on forever. And we can just distribute it into the function. So we have x cubed plus x fourth plus x to the 5th plus x to the 6th, go on forever. So what this really is this is just shifting the generating function over. So what we have here is, because we're shifting it by x cubed, we have zeros for the first 3, and then we have 1s for the rest. So that's how multiplication works. Again, it's not too complicated. So if I say, okay, I want x to the 6th of x cubed over 1 minus x, this is really the same thing as saying I want x of 6 minus 3 times 1 over 1 minus x, because all we did was we shifted over by 3 powers. So when we take the coefficient, we just need to shift it back 3. So x to the 6th, or the coefficient of x to the 6th of x cubed over 1 minus x, is really the same thing as saying I want x cubed of 1 over 1 minus x. This is a very useful skill that will be used in further examples. So here's the final question. What is the generating function for x1 plus x2 plus x3 equals cubed of 1 over 1 minus x? This is a very useful skill that will be, okay, I want x to the 6th of x cubed over 1 minus x. This is really the same thing as saying I want x of 6 minus 3 times 1 over 1 minus x, because all we did was we shifted over by 3 powers. So when we take the coefficient, we just need to shift it back 3. So x to the 6th, or the coefficient of x to the 6th of x cubed over 1 minus x, is really the same thing as saying I want x cubed of 1 over 1 minus x. This is a very useful skill that will be used in further examples. So here's the final question. What is the generating function for x1 plus x2 plus x3 equals 12 with a couple more restrictions? x1 has to be greater than 2, x2 has to be between 3 and 6, and x3 has to be less than or equal to 9. Well, this could be very challenging using inclusion-exclusion, but we can make this pretty simple, just doing it with generating functions. So x1 has to be bigger than 2, so this just means it's x squared plus x cubed plus x fourth, and we can take it forever because it doesn't matter how high we go, because if we have x27, well, it's never going to add up to x12 or multiply to x12, so we don't need to worry about it. x2 has to be between 3 and 6, so let's do that one in light green. So here we start at x cubed, and we just go up to x fourth plus x5 plus x6. Okay, that's as far as it can go. And this next one has to be below x to the 9, so we can start with 1 plus x squared all the way up to x to the 9. So that's our generating function. Well, it's a few formal power series. We can simplify this. So here's what we'll do. We're going to take x squared out of the first series, so that way we start at 1, and well, we know what this generating function is, so this is just going to be x squared times 1 over 1 minus x, which was just the same thing as x squared over 1 minus x. So these are all equivalent. With this next generating function, we can just take out an x cubed, and we'll have 1 plus x squared plus x cubed. And if you remember from before, this is the same thing as x cubed times 1 minus x to the 4 over 1 minus x. Again, you'll need to do a few practice problems in order to memorize these things and get them right. Right? So this doesn't really need to be simplified at all, but what we can do is we can just sort of put the coefficients out front. So we could make this x to the 5 instead of x squared. And then we'll multiply by 1 minus x to the 4 over 1 minus x. And this last one, well, we only want to go up to x to the 9, so this is just going to be 1 minus x to the 10 over 1 minus x. So that's the generating function for x1 plus x2 plus x3 is equal to 12 with those conditions. Of course, how do we find coefficients? Well, we're going to get to that in the next video and the video after that, but you now have the basics to turn any counting problem into a generating function. So hopefully this helped. I definitely recommend going online, finding practice problems for this, and just getting used to turning these questions into generating functions. These are very popular questions. The coefficient changes, having n cents going into something.
Hello, welcome back to Discrete Calculus with the Wolfram Language. I'm Alistair Forsyth, and this video will be all about generating functions. So a generating function is an infinite power series whose coefficients are the elements of a corresponding sequence. For example, when given the sequence a sub 0, a sub 1, a sub 2, and so on and so forth up to a sub n, we could write the generating series big A of x, which would then be equal to a sub 0 plus a sub 1 x plus a sub 2 x squared, and so on and so forth. Overall, big A of x will be equivalent to the infinite sum starting at n equals 0 of a sub n times x to the power of n. When working with a generating function, the variable x in big A of x is called the auxiliary variable. Sometimes people say big A of x enumerates the sequence a sub n. Along with that, when working with generating functions, people often use the notation of x to the power of n in brackets, big A of x, as the coefficient of x to the power of n in big A of x. Now, there are actually a handful of different types of generating functions, but in this lesson we'll focus on ordinary generating functions. Now, I want to take a moment here to address that many of the examples used in this lesson, and many of our other lessons, come from Concrete Mathematics by Ronald Graham, Donald Knuth, and Orrin Potashnik. I would say Concrete Mathematics is easily the best textbook I have ever read, and I would heavily recommend checking out a copy if you enjoy this course. It's definitely not an easy read, but it's certainly worth the time you put into it. Now, before we look at the main properties of generating functions, there's actually two different applications we can see right off the bat. Firstly, the binomial theorem shows us a generating function for the binomial coefficient of n, k in terms of k. To put it fresh in our minds, the binomial theorem shows x plus y to the power of n will equal the sum from k equals 0 to k equals n of the binomial coefficient of n, k times x to the power of n minus k times y to the power of k. According to the binomial theorem, 1 plus x to the power of n is equal to the sum from k equals 0 to k equals n of the binomial coefficient of n, k times
I'm back. Wow. Okay. What art? Go art. Okay. Where's my phone? Where's my phone at? So bad. But we roll. It's bad, but we roll. Yeah, we roll, bro, we roll. It's terrible. It's terrible, absolute disaster. But we have to roll. Just the process. Trust the process, even though I know it will not be good. You have to trust the process. What in the bow-legged? Bow-legged, You will trust the process, bro. You will trust the process. Oh, man. Shifted. Bow-legged. So bad. Okay.
times x to the power of k, making 1 plus x to the power of n a generating function for the binomial coefficient of n, k. Similarly, a generating function for the binomial coefficient of n, k in terms of n can be found as x to the power of n divided by 1 minus x to the power of n plus 1, which is then equal to the sum from k equals 0 to k equals n of the binomial coefficient of k, n times x to the power of k. Along with that, we can use generating functions to demonstrate an application of the Fibonacci numbers that we covered in a previous video. The question was, how many different ways can you cover a 2 by n rectangle with 2 by 1 dominoes? To answer this, we'll start by examining the base cases. When n equals 1, our number of ways will also be 1, as you can only cover a 2 by 1 rectangle in one way with 2 by 1 dominoes. When n equals 2, t will also equal 2, as you can either cover the space with horizontally placed dominoes or vertically placed dominoes. Building off of that, when n equals 3, t will also equal 3, as you can add a vertically placed domino to either configuration of n equals 2. To clarify why this is 3, there are two ways to add a vertically placed domino to the horizontally placed configuration of n equals 2, whereas there's only one way to add a vertically placed domino to a vertically placed configuration of n equals 2. Now this seems like it's starting to build a recurrence relation of t sub n is equal to t sub n minus 1 plus 1. However, this is broken when you consider that when n equals 4, t equals 5, as you can either have two variations of n equals 2 together or add a vertical domino to n equals 3. Now if any of these base cases are confusing to you, try writing out every configuration for n equals 1, 2, 3, and 4 by hand on a piece of paper with a pencil, as there was only 11 configurations and it'll make understanding the rest of this proof much easier. From here, we can notice the pattern that t sub n is then equal to t sub n minus 1 plus t sub n minus 2. Running through this, we can verify that t sub 3 is equal to 1 plus 2, which is 3, and t sub 4 is equal to 3 plus 2, which is 5. Now to justify this as n grows without bounds, we can see that the left term of t sub n can be two horizontal dominoes added to a variation of t sub n minus 2, or the left term of t sub n could also be a vertical domino added to a variation of t sub n minus 1. This means that we can create a new variation of t sub n from any variation of t sub n minus 1, or from any variation of t plus two horizontal sequence, alpha times f of x plus beta times g of x. We'll just take that coefficient and separate it out of the sum.